Hello, everyone. Let's continue with the second part of today's lecture. So the next, we are going to discuss the orbital elements and the state vector. So recall, when we focus on the motion in the two-dimensional orbital plane, we only need two parameters to define the orbital plane. One is the eccentricity, another is the angular momentum. However, now if we expand the dimension to 3 dimensionals, we need extra elements to define the location of the orbital plane. So we will insert another figure here. So from this figure, as you can see, in addition to the previous two parameters like eccentricity and angular momentum, we have additional parameters defined here. So first, we locate the intersection of the orbital plane with the equatorial plane. So the equatorial plane is a shadowed area, and the intersection of the equatorial plane and the orbital plane, they intersect at a point, at a line. We call it this line as a node line. The point on the node line where the orbit passes above the equatorial plane from below, it is called the ascending node. That's this one. Ascending node. As you can see, this node 9 vector n, we labeled here. It extends outwards from the origin through the ascending node. At the other end of the node 9, where the orbit dives below the equatorial plane, is the descending node, which is the opposite dashed line. We labeled on the plot. So the angle between the positive x-axis and the node 9 is the first Euler angle, omega, which is labeled here. The right ascension of the ascending node, we also call it the right ascension of the ascending node. And this angle, omega here, it can change from 316 degrees to 0. And this another angle between the orbital plane and the equatorial plane is the inclination angle, I, we labeled here. It measured according to the right-hand rule, that is counterclockwise, around the node 9 vector from the equator to the orbits. So again, the shadowed line from the equator to the orbits, we get the ascending node. Oh, sorry, we get the inclination angle. The inclination angle is also the angle between the positive z-axis and the normal to the plane of the orbit. So from the definition of the angular momentum, which is normal to the plane of the orbit, we can get this equivalent relationship. And this angle I, its range is from 0 to 118 degrees. Now next, we need to locate the perigee of the orbit. From the perigee and the true anatomy, we can get the position of the satellite on the orbital plane. But where is the perigee? Then we introduce another angle. We call it the argument of perigee. This is the angle between the node line vector n and the eccentricity vector e. So eccentricity vector e is pointing from the center in the geocentric coordinate to the perigee. And the angle between the node line and the eccentricity vector is called the argument of perigee. And this argument of perigee is the number between 0 and 316 degrees. So we use omega to represent this angle. So to better illustrate the orbital elements, we may use the movie again. So the movie I find, it's first, we will see animation that defines the orbital elements. So it's the semi-major axis first. It defines the size. The next, the eccentricity that defines the shape of the orbital plane. So this is just two-dimensional. So next, we define the inclination. That's the angle. Rise from the node 9 to the orbital plane, and rotation from the polar axis to the node 9. Let's come back. I'm a little bit slow. So we have right ascension, the argument of perigee. And the true anatomy. So I also have another movie explains the
in this
orbital
image,
elements.
I have drawn it in 3D format.
So this movie tells us how we define the additional 4 elements after we get the eccentricity and angular momentum. That's only in the 2-dimensional space. To define the location of the orbital plane, we introduce another 4 elements. So this movie gives exactly similar definition, and it defines in a dynamic way, so maybe it will have better explanation. Let's see this movie.
It can be a little tricky because I am depicting a 3D orbit or a 3D concept on basically a 2D screen. But here we see the blue Earth, and the center of the Earth has 2 axes going through it. One here, or actually let's start with this one here that goes through the north and the south poles, the north-south pole axis, or the axis of the poles, and this one here, which is a seemingly arbitrary axis because it is an arbitrary axis, and it points to the vernal equinox. Vernal equinox. The gray plane here is the one that passes through the equator of the Earth and is known as the equatorial plane. Equatorial plane. Similarly, the orbit also passes through its own plane, the red one, known as the orbital plane. Notice here that the orbital plane intersects the equatorial plane, forming a line of intersection, where there are 2 points where an object going this way across this point here will tend to cross the equatorial plane, ascending from below to above it. This point is known therefore as the ascending node. Ascending node. Similarly, on the other side, the object will descend to below the equatorial plane, and this point therefore is known as the descending node. If here I hold the Earth and the equatorial plane and the north-south pole axis steady, or the north-south pole axis steady and the line that joins the 2 nodes steady, what I can do is I can change the tilt of this orbit around this line that connects the 2 nodes, either by tilting it this way or rotating it this way or rotating it the other way or this way. This determines the angle between the orbital plane and the equatorial plane, that angle there, and that is our third parameter, that which determines the tilt of the orbit. The parameter itself is known as inclination, denoted by the letter I, measured in degrees from the equatorial plane to the orbital plane. Notice here that there is another angle. If I hold the Earth and the equatorial plane as well as the north-south pole axis steady, I can, without changing this tilt angle, I can simply swivel this orbit around the North Pole one way or the other way, thereby shifting both the nodes this way or that way, depending on how I tilt or swivel this orbit. And this is the fourth parameter, that which determines the swivel of the orbit. How do we measure it? Notice that the swivel changes this angle from the vernal equinox to the ascending node, that angle there. That angle is known as the longitude of the ascending node. It is denoted by the capital Greek letter omega, measured in degrees along the equatorial plane from the vernal equinox to the ascending node. We have determined the size and the shape as well as the orientation. So we have completely determined the orbit itself. But if there is an object in this orbit, we still haven't figured out how to position it and how to locate it. We'll do that now. Notice in this cleaner picture again the 2 nodes, and this looks like it would be the periapsis, the closest point of closest approach, and similarly that one over there will be the point of furthest approach. Suppose that there is an object in this orbit at this location going this way. It is approaching the apoapsis and has already passed the periapsis. But where is the periapsis in the orbit? I can hold everything steady, including the nodes and the equatorial plane and the inclination, and I can change the length and the width of the orbit to determine where this periapsis lies. It could basically lie here, or say here. Suppose that it lies here. If you notice that it makes an angle in the orbital plane from the line that joins the ascending node to the center of the Earth, all the way to the line that joins the periapsis to the center of the Earth. That angle there. That angle is our fifth element, and this determines the location of the periapsis. The location. And the nomenclature is the argument of the periapsis. And it is denoted by the letter omega in its lowercase form, measured in degrees, this time in the orbital plane, not in the equatorial plane, from the line of the ascending node to the periapsis radius, always in a counterclockwise direction when measured from the North Pole. So counterclockwise that way, as you can see. Now we have determined where the location of the periapsis is, but where is the location of the body? That is, where is the body positioned in this orbit? Notice that if this is the periapsis, so we'll erase that point. Suppose that this is the periapsis here, denoted by the asterisk. Now the body has crossed the periapsis, and it also forms an angle from the line of the radius of the periapsis to the line that joins the center of the body to the center of the Earth itself. That is this angle there. And this is our sixth element, the position of the object in the orbit itself. And this angle is known as true anomaly, denoted by the letter mu, again measured in degrees, again in the orbital plane, from the line or the radius of the periapsis counterclockwise in the orbital plane to actually where the body is positioned. So we have determined.
Okay, so we use 2 videos to explain the 6 orbital elements. And as you can see, with those 6 orbit elements, we should be able to do one thing. This thing is we can use the R vector and the V vector to find the 6 orbit element. The H, E, I, omega, and the small omega, theta. And we can do the reverse way, using the 6 elements to get the position vector and the velocity vector. However, there is no methods explained before how to make those conversions. And now, I think with the 2 movies, we already very clear how the 6 elements are defined. The next, we will talk about the mathematical computation that explains the conversion between the 2 different sets of elements. We will do the first one, that is using the velocity vector, position vector, to find H, E, I, omega, small omega, theta. And it includes several steps, and those are included as algorithm in the book. But it's necessary for us to know the detailed step first. So step 1. Step 1, we will first calculate the magnitude of R, which is also equivalent to x squared plus y squared plus z squared and square root. Since in the geocentric we all use capital letters, so I will change the y into capital letters. And we will do the same thing for the velocity vector, v. So the v magnitude equivalent to square root of v dot vector. It's also equivalent to the v x squared plus vy squared plus the vz squared and the square root of the summation. And the next, step 3. After we calculate the v magnitude, we can get the radial velocity. Remember the definition of radial velocity, the VR. It's equivalent to the magnitude of v times its unit vector in the r direction. And we can also get it from the r vector times v vector divided by the magnitude of r. And step 4, we are going to calculate the angular momentum, which is very straightforward. We just use the r cross v. Then step 5, we can get the magnitude of the angular momentum. From step 4, we get the vector of the angular momentum. Then the magnitude of angular momentum is simply h vector times h vector and get the square root of them. And then the inclination. If you recall, we said the inclination here is the angle between the ascending node and the orbital plane. We also said this is because the angular momentum vector is normal to the orbital plane. Therefore, the inclination angle I is also the angle between the positive z-axis and the h vector. So step 6. Between the z-axis and the h vector. Therefore, the step 6, based on this observation, the I equivalent to hz divided by h, and we get its inverse cosine. And we already defined the I is between 0 to 118 degrees. So that will give us the determinant value of I. There is no the quadrant ambiguity here. So step 6 gives us the I value. Step 7, we will continue. Since we get the angular momentum, then the ascending node n equivalent to the key unit vector time across the edge, according to the right-hand rule. The ascending node should be perpendicular to the k and h, and that will give us the vector defining the ascending node. Since we get its vector, we are not far away of getting the relative omega angle. So we will get the magnitude of n equivalent to n vector times n vector and the square root of this. And then the omega angle equivalent to the cosine inverse nx divided by n. And we also know the omega should be in the ascending node, lying on the positive side of the vertical x z-plane if omega is between 0 and 180. That is the ny. Larger equals than 0. And if it's a negative, less than 0, then the omega value will be equivalent to 316 minus this. So here we should identify the range of their quadrant. This is step 9. And step 10, we are going to use the eccentricity vector, E vector. If you check the book of chapter 2, in chapter 2, when we integrate the constant value of the angular momentum, we have the definition of the eccentricity vector, which is equivalent to 1 divided by mu v cross h minus mu r vector divided by the r magnitude. And we can rewrite it equivalent to the v square minus mu divided by r vector minus r vr v vector. And since we get the magnitude, the eccentricity vector, we can easily get the eccentricity, its magnitude. So E is magnitude equivalent to vector E times vector E and its square root. So now you see, let's check. It seems that we already get 4 elements so far. The only 2 elements that has not been identified is the argument of parity and the true anonymy. And we can find the argument of parity again. Argument of parity similar to the omega. It is in the range of 0 and 316 degrees. So we need to identify which quadrant they belong to. So the omega is defined by the ascending node and the eccentricity vector divided by the n times the E magnitude. And that requires us to identify their quadrant according to the EZ value. So if the EZ value is larger or equal than 0, it is in the first or second quadrant. And if EZ, so EZ here means the third element in the Z vector. If it's less than 0, omega equivalent to 316 minus inverse of cosine n vector times E vector divided by the NE magnitude. Now, the only unknown vector, the only unknown elements we haven't defined is the true anonymy. And the true anonymy, as you can see from this definition, theta, it can be any angle between 0 and 316 degrees. So we also need to identify its quadrant. The angle of theta here is defined by the E vector and R vector. So the E here is along the line from the center to the periapsis, and then from this line to the angle to the R vector, we find the angle between them using the dot product. And if VR is larger or equal than 0, we get the theta value should in 0 or 100, between 0 and 100 degrees, and the reverse side. When the VR is less than 0, we have another definition. And this E and R vector can be expanded. As we know here, we can expand this and write this as an expanded term. So using the 13 steps, we can find the 6 orbital elements from the position and the velocity vector of an object on the orbital plane. Okay, we will take another short break and come back soon.